Two. Okay, super. Okay. So we're now live. Okay. If you object to being potentially recorded, please say so now. But otherwise, we're truly delighted to have Francesco Petruccione here to visit us and talk to us today about quantum computing. So for some slight background, so Francesco relatively recently moved to University of Stellenbosch from UKZN, where he was the Vice-Chancellor of Big Data and Informatics, also was a professor, full professor at UKZN, now full professor at Stellenbosch, also is the interim director for the National Institute for Theoretical and Computational Sciences, a highly regarded member of the Academy of Science of South Africa and a fellow of the Royal Society of South Africa. Literally wrote the book on open quantum systems, and currently has over 25,000 citations in an H-index of 50 to your name according to Google Scholar. So truly honored and deeply appreciative of you coming to talk to us today.
Wonderful. Thank you very much. Thank you. This is always very interesting what Google Scholar says. Yeah. No, thank you very much. I hope you won't be. So thank you for the introduction. I hope you won't be disappointed because I was asked to prepare a kind of a double set of lectures. Yeah. And the first one was supposed to be easy, so this will be very easy. So if it is so easy, we can go and have a coffee. Yeah.
And you're open to questions as you go.
Yes, yeah. And the second one, I thought we will see what you asked, and then I can see what we can organize for next week or whatever the next talk will be. Yeah. Yes. So the plan. Yeah. Very briefly, maybe some introductory remarks, and in particular, I also want to very briefly mention what is going on in South Africa in quantum computing. Yeah, just so that you know, in case you don't know. The second point we might skip, depending how I gave you expressions. If you are bored, I will just skip. Then, I will just give you a very brief overview of what out there, what you can do with quantum computers. And then I will discuss briefly this supremacy, which is a horrible word, that then became advantage, and now it became practicality. Yeah. And who knows what will become next year. Yeah? And then I will describe some of the things that maybe quantum computing should try to solve. Yeah? And we are sort of engaged in one of those. Huh? These days, you can't do anything. Yeah, so you can ask ChatGPT, explain quantum computing in a sentence of 5-year-old. Quantum computing is magical. Yeah. Can do many things at once, much faster than a regular computer, using tiny particles that can be in two places at the same time. So that's the end of the talk. Yeah. Then you can become a little bit more ambitious and you ask ChatGPT again to do an elevator pitch for a quantum computing startup. Yeah, and okay, suggest even a name. Revolutionizing the future of computing, cutting-edge technology, blah, 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 blah. Breakthroughs, medicine, finance, AI, and more. Quantum revolution, transform the landscape. If you go to Amazon and you ask them, other books on quantum computing, the Quantum Spark, a very interesting book. Yeah. Very, very realistic because the biggest competitors in quantum computing are the US and China. Yeah? China is the only country that has several quantum-enabled satellites to do secure quantum communication. Nobody else does. Yeah? And the US are pushing very hard in quantum computing as well. Yeah? I'm very proud owner of a Thriller index of 1. But I don't know how many of you have been mentioned personally. Okay. Yeah, so that's it. Yeah, very interesting thriller as well. Unfortunately, the guy who read that paper dies a few pages later. Yeah, so our turn. Yeah. Yeah. So other things to read. Since 2 years, I think it was 2021, almost 3 years because yeah, end of 2020. We have an official South African Quantum Technology Initiative, yeah, which is also built on the model of that NRF and the SILI of a consortium, yeah, and a consortium of those 5 universities. And it's based around, let's say, 3 pillars. One is quantum computing, one is quantum communication, and one is quantum systems. And there are also other things that belong to quantum technology, but those are the ones, like for instance, you can do quantum effects in biological systems and things like that, but you can push them in one of those things. Yeah? At least that is the plan. Yeah? And this SAQT, the website is down there, has also opportunity in terms of bursaries and funding for events and things like that. So every now and then, you look at the website and try to engage with it. Yeah. NITheCS does also quantum technology. We have a research program with some people that I suppose to meet here. Yeah, also involved, and others, of course. These are the PIs of this research program. Yeah, and so that there is possibilities of funding there as well. Yeah. Recently, we joined QWorld, yeah, and we became a UKZN as South Africa. So QWorld is a non-profit organization that essentially introduces whoever wants to quantum computing. Yeah, it's a little bit like the carpenters. I don't know if you know the carpenters. The carpenters is another NGO that offers courses free of charge to everybody in data science, programming, bioinformatics, all things programming. Yeah. And this is the same system for, more or less the same system for quantum computing. And if a country joins QWorld, it becomes a QKAS. Yeah, so South Africa, since a month or so, is a QKAS. Yeah, and there are again educational programs that you see there on the right side. And in fact, at the beginning of July, we had the first. They call it the entangling event when you join QWorld, and we did an online introductory course to quantum computing, and we had more than 250 participants, of which more than half were from South Africa. There were also other people from the rest of Africa. So that there's definitely a need for that. No, if you go to the website, there's a link to a GitHub repository with lots of training material, Jupyter notebooks, blah, blah, blah. So you can do it also yourself without attending one of the courses. Yeah. So now, quantum computing. Quantum processing, if you want, is manipulating information with quantum physics. Yeah? And and this business started in the early 80s with the famous man, yeah, who had somehow the intuition that if you want to simulate the nature of the quantum level, if you had a quantum machine that does it, it's probably right there. Yeah? And that was the good idea. Yeah? And now, eventually, we are getting there. Yeah? But let me give you a brief history. Yeah? Quantum mechanics started around 1900s. Yeah, Schrödinger equation in the 20s. Yeah? And sorry, I have a few milestones that have nothing to do with quantum, but just to remind you what happened in classical information theory. Yeah, Turing was in the 30s. Yeah, with the universal Turing machine. It took 30 years from quantum mechanics to the transistor. Yeah. And interestingly, after the Second War, we had also Shannon, mathematical theory of information. Yeah. And all those things are related to trying to hack the Nazi codes in the Second War. Otherwise, maybe we would have taken on this one. Yeah. The interesting for quantum computing, interesting aspect is these early 70s, early 80s. Yeah, where for the first time, people like Paul Demel, Violence, Harosh, they all got the Nobel Prize. managed to manipulate single quantum objects, single atoms, traps, single ions, and things like that. Yeah. Because until then, you know, the hydrogen atom in the third year functional mechanics said the textbook didn't really exist. I mean, it was there, but nobody had seen it. Nobody could manipulate it. Yeah. Only 50 years ago, we started having the.
Yeah.
Feynman I mentioned before. Yeah. Soon after, David Deutsch. So I don't know why this thing is blocking the view here, but anyway. What should I do? maybe you can answer. Yeah. Anyway, okay, you see the face of David Deutsch in Oxford. He did essentially what Turing did for the classical computer, for the quantum computer, showing that in principle, some machine here and there. Yeah? But it was more a theoretical curiosity, because nobody knew what you could do with such a machine. Yeah? The big breakthrough was in the 90s, yeah? Essentially due to Peter Shor, yeah? Who showed that you can develop an algorithm to factorize into prime numbers. Yeah? And that is a big thing, because all of a sudden you could build a machine that can crack the RSA. The same Shor, a few years later, came up with an algorithm for error correction. Yeah? And that was really critical, because if you want to build a quantum computer, like if you build a classical computer, yeah? Without error correction, it wouldn't make much sense. Huh?
Yes, we can stand a bit closer to the mic.
Sorry, I was drifting. Yeah, okay, sorry, I'm here. Yeah. And in between, there are other algorithms proposed, like a search algorithm, things like that. Yeah? Only towards the beginning of this millennium, yeah, the first practical realization of a 2-qubit quantum computer using NMR technology was achieved. Yeah? And that is, of course, a technology that was very good to demonstrate the proof of principle. But you know, if your aim is to have millions of qubits, it's not really the way to go. And since 5-6 years, IBM puts these quantum computers that they produce in the cloud. Okay, so this is in a nutshell. Now comes the part where sorry, I'm going too fast. Where probably boring. You know all these things. You know what a qubit is. Yes. So we don't have to. Sorry, I use part of this talk at the SAIP winter school. Yeah? So we don't need to do these things. Yeah? I mean, once you have a qubit, you want to do things. Yeah? And it is typical quantum computing picture. You use gates, yeah, that are unitary objects to do various operations. And since the qubit is two-dimensional, the gates are 2 times 2 matrices and can do bit flip, phase flip. We can even create superpositions with a Hadamard gate. Yeah. Okay. In principle, yeah, and here's another wider collection of gates. Yeah. In order to build a quantum computer, you need to be able to implement in hardware the X, Y, and Z. Yeah, and the CNOT. Yeah, that's the minimum requirement to build a quantum computer. Yeah? If you have those three, and the famous theorem and blah blah blah. Yeah? If you have those three single qubit gates and a CNOT as a control NOT as a 2-qubit gate, in principle, you can build all the manipulations you need on a quantum computer. Yeah? Technically, sometimes it's more difficult because depending on the hardware, you might not have access to those. Yeah, but in principle, that's the so that the quantum computer looks like that. You have qubits as input, a big unitary machinery, and you measure, and that's it. In practice, you need to do a few more things, because you need to do like if you build a classical computer, you need to do a full stack kind of development. Yeah, from the qubits to the system software to the application software and so on and so forth. Yeah? And each of these blocks is a discipline on itself. Yeah, in the meantime. Yeah. I will just speak at the very somewhere at the very top. No, the hardware is all very technically challenging business. Yeah? Otherwise, we would already have universal quantum computers. Yeah? So this is the what you need to do. Yeah? Software-wise, and now I'm speaking again at the very top. Yeah? You know, it's a little bit, the situation is a little bit like when the first cars were produced. Yeah? There are lots of people, there are hundreds of startups and big companies that work on this, and everyone thinks they do it better. Yeah? At some stage, you know, we'll end up with 4 or 5 providers of quantum computing and quantum hardware and software. Yeah? Because probably not all of them will survive. Yeah? So so every major company that has something to do with computing has its own preferred software development package. Yeah? I won't speak about D-Wave because that's a different architecture. It's more of an annealing kind of thing. But there are open source projects. IBM promotes Qiskit. Rigetti, which is one of the first hardware startups, has something called Forest. Microsoft promotes QSharp. Yeah? Instead of C#. And nobody used C#. Nobody used QSharp. Yeah? And Google has CIRP, which is also something. But most of it, except for QSharp, most of it is sort of Python based or inspired. Yeah, please. Which do you prefer? Which I prefer. I prefer Julia. Yeah. No, and the reason is very simple. Sorry, I just discovered a typo. The reason is very simple. You know, it's fun to access this existing quantum computer in the cloud. Yeah? And through IBM, you have also free access to 5 qubits, 10 qubits, 20 qubits. Yeah? But it takes a lot of time to run the code on the quantum because you spend a week in the team. Yeah? And the reality is, if you have a desktop with a good GPU, you can do almost 30 qubits easy. Yeah? If you do it in Julia, if you do it in Python, it's worse than waiting for the quantum computer because Python is not very slow. So that's the reason. Yeah? But then you can convert and it's not a problem. Yeah? So what's next? Okay, officially, we are now in what John Preskill called the noisy intermediate scale quantum computer epoch. Yeah? Mainly because at that time, a few years ago, he was speaking 50, 100 qubits. Now that I will show just now how many we have at the moment. Yeah? They're just small, yeah, and there is no error correction. Because to do error correction, you need lots of qubits that we don't have. Yeah? So this is essentially you calculation without a safety net. Yeah? And you know, you can play with a 10 qubit IBM machine, and you do random sequence of nodes after 5 layers, it's just random. Yeah, that's the real, more or less. Huh? Sorry, I shouldn't mention providers. Yeah. So what is the technology? Yeah. There are, and this is again one reason why in this famous South African quantum technology roadmap, we intentionally decided that we won't have the ambition to build our own quantum computer at this stage. Yeah? Because you need hundreds of millions of dollars. And if you're unlucky, you put all your money on that. So it's, first, we don't have that kind of money because you need to have a budget like the SKA. Yeah. And second, you might need to money. So it's a little bit of a risky business. And you know, in these days, everything is a cloud anyway. So for practical purpose. So some of the big players, IBM and Google, Rigetti is a startup, bet on superconducting qubits. Yeah. Other bet on trapped ions, and these are all newer companies. Yeah. Neutral atoms, photonics. Yeah. Is also very interesting. Intel works on silicon, spin-based silicon. They use the Intel silicon technology for spin-based manipulation of qubits. And then, sorry, I thought I was already further. According to that gentleman up there, Naven, who is the quantum guru of Google, he invented Neven's law, claiming that quantum computers at the moment are improving at a double exponential rate. Yeah, whether that can go on forever, it's a different story. Yeah? Also because soon we are at the into the power 275. Yeah? You are quite a large number. Yeah, but these are the I guess when they raise hundreds of millions, these are the slides that they show to their investors. Yeah?
Sorry, so just a quick question.
Please.
The left-hand side is the number of qubit, right?
Yeah, that's the dimension of the Hilbert space. Yeah.
So, if I try to compare this to Moore's law, because obviously it's similar. So Moore's law is about packing a number of transistors onto a wafer.
Yes, but it's not double exponential.
Yeah. So how many transistors are on a wafer? How does that number compare to the number of qubits required to get to the top of the y-axis here?
I mean, if you have 100, you already have 10 to the 16. The vision is to have 1 million qubits. You should have a universal quantum computer able to do error correction and everything. Yeah. I mean, now we are somewhere here. Yeah, more or less. Yeah. I have, I think, the next slide shows you where we are now. Yeah. So this is, when we started IBM, it was just 1-2 qubit machine. I mean, today, if you want to buy a 2 qubit machine, there is a Chinese company called SpinQ, and for $20,000 or $30,000 sells it to you. You can put it on the desk. But probably, if you spend some time developing an app, you could simulate it on your phone. And maybe on the watch. It sounds a little cheaper. Probably, yeah. So now I think the biggest processor by IBM has 400 qubits. Yeah? That is the where we are at the moment. And this is just, if you go to Wikipedia, there's of course a page with all the processor, blah, blah, blah. But the latest one, Xanadu, is a Canadian startup, and one of my former students works there, builds photonic-based quantum computers. Yeah? They have claimed to have 216. Yeah? Intel, who develops this semiconductor-based technology, yeah, which has, of course, the advantage that the technology is already there, yeah? And also works at essential intelligence, which is also not to be neglected. They just have yeah. But that doesn't mean anything. IBM has 133, but I think they already revised down their roadmap, yeah? Because it's not so easy to scale up 1,000 or superconducting qubits. Lots of wires and lots of transistors that you need. And I will mention the reason for that just now. IonQ has 32. D-Wave have almost 6,000, but that's not a universal quantum computer. It's a dedicated annealer. Yeah, so you can only solve certain Hamiltonians and find them. So if you manage to map your problem on the Hamiltonian of the machine, it works very well. Yeah? And you can do very nicely optimization and minimization problems. And then there is Microsoft, has 1 qubit. Yeah, but a very interesting one. Yeah, because it's a topological qubit. Yeah, and the whole idea, and they published a few years ago, made a similar claim, but then they had to retract it because it didn't really work. Yeah? It was a little bit like what will happen to this superconductive through temperature paper line. I don't know. I know nothing about that. Yeah. So they are investing heavily in topological qubits. Yeah. And if you go on the let me see if I can run this. on the, does it work? Oh, why doesn't it work? So there's a very nice video on their website. I don't know why it doesn't work. Ah, now it works. Sorry. There is no audio, so no point in me explaining to you. They can do much better. Sorry for the, okay, this was not planned. That's not the reason why for that slide is critical. And I will discuss it later when I come back to practicality and things like that, is that the topological qubit, because it's topological, is way more stable than a superconducting qubit. Yeah. And second, you can manipulate it just by switching on and off a voltage. Yeah. The superconductor, which means it's essentially digital. Yeah, so you don't need lots of transistors behind the qubit to do whatever you have to do. Yeah. Whereas when they put a superconducting qubit, if you manipulate, you need microwave fields. Yeah, and those are not digital. So you need a ton of transistors first to prepare the signal and then to go to the signal and blah blah blah. So there's lots of electrons. So that's way more challenging to scale it down. So once you have a topological qubit, yeah, that's the claim of Microsoft. Yeah, it should be easier to scale it up to 1 million, just because you need less electronics to run the system, yeah, and make it faster. Yeah.
So they claim it seems like the mode is a Majorana mode, but
Yes.
have they actually measured it? Because I don't know that anybody's ever measured a Majorana mode before.
That is the claim of this paper.
Okay.
They already retracted. So I didn't redo this. Yeah. So I only know that this is published. Yeah. I don't know. You know, I'm also not an expert of topological qubits. That's not my really line of business. Yeah, but it's an interesting line of business for sure. Okay. So that was just to give you an idea roughly what software-wise and hardware-wise is out there. Now, quantum algorithms. Yeah, I mentioned a few in the little historical overview. Yeah, and here is just stolen from somewhere. Yeah, it's quoted behind talking guy. Yeah. A quick timeline of some of the most important ones. Yeah? It started with David Deutsch, we mentioned him before, yeah, who had a very simple 2-qubit algorithm to show that you can do something. Yeah? You can, in principle, parallelize something and have some quantum advantage of sorts. Yeah? Then quantum box, phase estimations. Yeah? The very important one I mentioned before, quantum error correction. Yeah? Somebody was mentioned, it's not in Fourier transform before we started. I don't remember this one now. And I'm glad that it's there because I forgot. Yeah, and so on and so forth. Yeah, but then you see in the last 10 years, there's a whole array of let's call it the more modern quantum computing algorithms, essentially specifically designed for these noisy quantum computers. Yeah. For instance, one of the most famous ones is variation of quantum solvers, yeah, which is a kind of a hybrid algorithm. You do a part on a quantum computer and do the optimization on a classical machine, and you hope that in the roots are defined the eigenvalue, mainly of some chemistry and material science problem. Yeah. That's where they're mostly applied, and also in machine learning, in the quantum version of machine learning. Yeah. And there is a lot of, so I don't have machine learning here, but that's also one of the things that people are hopefully hopeful that might be able to achieve. Yeah. If you want to see them all, yeah, there is a website called the Quantum Algorithm Zoo, yeah, which categorizes all algorithms in algebraic and number theoretic, oracular, approximation and simulation, and then optimization, numerics, and machine learning. And I don't know how many they have there, but there are 450 references. So certainly a couple of hundred different algorithms are.
You have to explain what the word oracle, what the place of the word oracle is in science.
Yeah, that's a trick that is used. You know, we mentioned this Deutsch algorithms. It is a trick that is used to do something.
So just a fancy name.
You use an additional few bits to play the role of the oracle, mainly by entangling it with something else. Yeah? Okay. But it is a category of this algorithm. Yeah? So there are hundreds of different algorithms. Yeah? But it's not like they are all independent from each other. Yeah? And this is just a simple attempt for some of these algorithms to show you that they are all related somehow. Yeah, you can have very simple components like quantum Fourier transform, which is a tool that you can use for a million things. Yeah, which you can then use to do other things, like to estimate the phase of something else, and that in turn you can use to do linear algebra. Yeah, so it's not, there is a kind of a hierarchy of different building blocks. Yeah, so it's not like if you do linear algebra, you have to start from scratch. Yeah? You can build upon things that others have done and slowly build it up. Yeah? So that's one of the things that, you know, if you teach a course in quantum computing, you need to find a way to build it up from the bottom. Yeah? So that's one of the things. Just to give you a taste, I mentioned this variation of quantum eigensolvers, yeah, which are very popular to solve ground states of molecules, yeah, essentially, yeah, in chemistry and material science. Yeah. And these are kind of a hybrid algorithm where you do one part on the quantum computer and you calculate the expectation value of whatever Hamiltonian you have, yeah, depending on some parameter. Yeah. You do then your optimization with respect to some cost function, change the value of the parameter, and do it again, and hope that it converges towards something. So this is a very popular choice of quantum algorithms these days. Yeah? So now to the part that I use to attract you here. Yeah, the supremacy, advantage, and practicality. Yeah? The first claim of quantum supremacy was done by Google together with NASA in 2019. Yeah? And they had a fairly artificial problem where essentially based on the sampling of the statistic produced as some random circuit program from their quantum computer. Yeah? And the claim was that to do the same sampling exercise on a classical computer would have taken years, and they could do it in hundreds of seconds. Yeah? That was yeah, but this is you know, it's a supremacy claim, but not a practicality claim. It's a problem about the solution of the problem. Yeah? And then, of course, others were deeply offended that the sense that they could do it classically and blah, blah, blah. But that's how science works. Yeah? But what is interesting, and this was on a 53 qubit machine. So there was a strong claim that you could save years and boil down years to 2 seconds. Just a year later, I think a Chinese group using a similar, using an optical based quantum computer, claimed that they had also some computational advantage. So people started getting more modest. From supremacy, they went to advantage, and they also claim improvement in efficiency or faster by a factor of 10 to the 14, which is certainly an impressive number. And the story continues. Then Xanadu, which is a Canadian quantum computing startup, you see, they can do something in millisecond, microsecond that would take 9,000 years. But again, it's always kind of, in this case, it's a boson sampling problem. It's always sampling. Quantum computers are probabilistic machines, so they're very good producing probability distributions. So that's what they are. One of the things that they are good at. This is very recent. This brings us to June, where this is a paper by IBM. Well, now they speak of utility, because they solved on one of their 127 noisy qubit processor an easing related problem. And this was very funny because look at the date. This was 13 June, published in Nature. No archive preprint existed. So people saw this only on the 15th of June. And on the 23rd or 26th of June, in the archive, they could do it better classically. So it's an interesting challenge. But that's how science works. You claim something, some is better, and some and it goes on and on. So that I don't want to speak negatively, but the real practicality breakthrough, is probably not yet really there. But it gets better and better.
How does the tensor network method compensate? Or what does it get right?
It approximates the entanglement very well.
Okay.
So obviously the problem is not super entangled. That you can create a tangled network kind of fairly good approximation and implement it very efficiently on a, I don't remember what, some GPU machine, something like that.
Highly parallel, but
Yeah. So the reason why people are still believe in quantum computers is that on paper, if you look at the potential speed up, there are several algorithms that have exponential speed up. And this is a slide copied by a colleague in Korea. And you see on the left is the classical scaling with increased complexity. And on the right is the quantum scaling, that just from the analysis of the complexity of the algorithm. And on the right, you see lots of logs and lots of squares that you don't see on the left. That's the reason why people are so excited. For instance, linear algebra is something that works very well. Exponential speed up in theory. Search algorithm of Grover, it's only a quadratic speed up. So you need just the square root of operations to find whatever you're looking for. So this is the reason.
Wait, what is NSK?
Sorry?
For the matrix inversion, the classical algorithm is NSK.
I don't remember. Where did you read it?
For matrix inversion, second to bottom in the classical algorithm.
I don't remember. Something on
separate variable.
Yes. And it's something. I don't remember. Sorry, I was looking in the text. Sorry, I don't remember some parameter. It doesn't matter. The point is the end. The point is the end. That is a constant maybe one is the rank of the matrix, the other, I don't know, something else. I don't remember, but I'm sure we can find out. Yeah, and you can, and if you look at, this is now machine learning problems, there are similar potential benefits, yeah, in the various support vector machine, neural networks, and so on and so forth, classification, and so on and so forth. Yeah? But the problem is to do it. Yeah? And here where it becomes interesting. Yeah? So I try to show you now that, you know, we know the potential speed up. Yeah, it could be exponential. Yeah, we know that ideally we want quantum supremacy, although that's a horrible word, quantum advantage or whatever. Yeah, but what we're struggling is to find quantum practicality. Yeah, what can we do now? Yeah, with these quantum computers. So there is no doubt that 10 years, 20 years from now we will have them. Yeah, because you know, it's to scale up the qubits is an engineering problem. It's not a fundamental problem. So at some stage, one of them, not theoretical, experimental, someone will do it. Yeah, there is no doubt about that. Yeah? the thing is not. Yeah? And there is a very interesting paper published very recently by Matthias Treuer and others. Matthias Treuer is the quantum guy of Microsoft. Yeah? He was at ETH in Zurich before, and I know him since many, many years. And he was in Stellenbosch 2 weeks ago. Yeah? That's where we learned about these things. Yeah, and he did the following. Yeah? He compared what you can do with a better desktop machine that you can buy today, with NVIDIA 800 GPU, which I think is a couple of years old. Yeah? There are probably better ones on the market. Yeah? And what could you do with 10,000? And now the important thing is logical qubits, not physical qubits. 10,000 error-corrected qubits, qubits that don't do mistakes. Yeah? Which means in reality 100,000, 500,000 physical qubits. Yeah? With assumption like 10 microseconds gate time to apply a gate, yeah, that can apply gates to all qubits at all time, and they're all completely connected. You know, if you look at the connectivity of IBM or Google chips, they're not all connected. Yeah, you need to be careful which qubit connects to which qubit, and so on and so forth. And if they're not connected, you need to swap around and blah, blah, blah. Yeah? So we don't have such a machine by far. Yeah, but this is the comparison that they have done. Yeah, and one of the bottlenecks. Yeah, and this is a serious problem. Yeah? That lots of people are working on, but there is no real efficient solution, is how to input data in the quantum computer and how to extract them. Yeah? Because, you know, the problems that we are mainly interested at the moment, in particular, if you think of machine learning application, is you have classical data and you want to input them in the quantum computer and do quantum machine. Yeah? But classical data these days, to be interesting, how many parameters are checking it? So how many data did it have? Yeah? You know, a few years ago, when we started looking into machine learning problems, I was invited to give a talk at Samsung in Korea. Yeah? And apparently there was their big data guru sitting in the room. And when I showed him that we were testing our quantum machine learning with the iris data set, yeah, he stood up and left me. Because it was just a ridiculous data set that nobody cares about. Yeah? At least if you are in that kind of line of business. Yeah. So, but the problem is now on a GPU like the one from NVIDIA that I mentioned before, you can do it at 10,000 gigabit per second. Yeah? You can input data. On a quantum computer like the one that you would like to have, yeah, you're probably lucky if you can do it with 1 gigabit per second. Yeah? I just state here now that in the paper there's a very detailed analysis, but no, that's beyond the scope of this talk. Yeah. So that at the moment, yeah, it looks like if you have problems that involve huge amount of data, don't do it on computer. I mean, it's still interesting to look for quantum machine learning algorithms, yeah? But not hoping to compete with OpenAI or with Bing Chat or Bard or whatever they are called. Yeah, that's not realistic at the moment. So the hope is then to solve problems that have small data. Yeah, and that is typically simulation. Yeah? So going back to what Feynman wanted to do. Yeah, that is something where already these days we can do have some benefits. Yeah? The interesting thing also from this paper, I could have sent you the reference. Stay at home. What they did is the following. Yeah? They tried to find the crossover point where the quantum computer, that fictitious quantum computer, will beat the NVIDIA GPU. Yeah? And they gave themselves as target, it should be better on a time scale of 2 weeks computing time. Yeah? Because you want to solve real critical problems, big problems. Yeah? So that the crossover time is 2 weeks. Yeah? The quantum computer is the yellow line, and the blue line is the classical computer, and on the x-axis is the increase of problem size. Yeah? The problem is the following: yeah, that quantum you have, and this is kind of logarithmic, yeah, is of course exponential speed up. Yeah? So at some stage it will be better. Yeah? The problem is that operation on a quantum computer, because of the gates, yeah, are much slower, yeah, than flipping a bit on a transistor or a GPU. Yeah, yeah? So that there is the more operation you need to do the quantum computer, the slower it gets. Yeah? So there is definitely a crossover point. Yeah, and this is the computer form, yeah, of quantum versus GPU. Yeah. You see, GPU can do, let's say, floating point operations at 200 teraflops per second. Yeah? Quantum computer, 10 kilo operations per second. Yeah? So it's really slower. Yeah? It's really slower by order of magnitude. So you really need to be able to solve the same problem doing much less operations. Yeah, that's the only chance you have to beat the classical computer. Yeah? So what it means, and here again, I just showed the result of this paper. For instance, Grover has quadratic speed up. Yeah, and the quadratic speed up, if you reverse engineer it in the previous line, won't be enough to beat the classical computer in 2 weeks. Yeah? You need at least a quartic speed up. Yeah? So, in other words, if you don't have a built-in exponential speed up, with how we see now that the technology develops, it will take a little while to beat the classical computer. Yeah? You will beat it eventually, and these are just estimates. I think the motivation of this paper was mainly to bring a little bit of reason in this supremacy in business. Yeah, it could well be that at some stage these numbers increase by orders of magnitude because some clever engineer comes up with that is, and then of course everything changes again. Yeah, but so the really interesting lesson is that you really need to be, if you invest a lot of time to develop an algorithm that is only quadratic in speed up, it will take a long time before it is useful for anything. Yeah? Please.
So couldn't the more practical advantage be that you're using the near-term quantum computers to come up with algorithms that you haven't really thought of on a
Yes,
classical
yes,
computer,
yes,
and then just simulate that circuit on a classical one.
Yes,
better.
yes. No, no,
So overall, you have a better algorithm. than
Yes.
previous.
That's what will also happening. There are lots of quantum inspired algorithms. And that's why this hybrid algorithm is very valuable, because you do the part that the quantum computer is good at, you do it on the quantum computer, and the part that the quantum computer is not so good at, you do it classical. Yeah? That's the use that people do at the moment. Yeah. Yeah, so this is the state of the nation. Yeah. So again, essentially, if you want to use them, it's better to look at problems that have small data, but a really strong speed up. Yeah. So that from the practical point of view, yeah, it's just simulation that will be probably the area that will lead to quantum supremacy or quantum advantage in the near to medium term time scale. Yeah. And quantum chemistry, material science, simulation of quantum system, cryptanalysis, these kind of problems are really well suited for quantum computing. There are not hundreds, but there are lots of startups that develop software for drug discovery, protein folding, all those kind of things, because there's really hope that companies like Hyundai, they also store quantum computing to design better batteries for the cars. So people are really using all that. Yeah. Machine learning, because of the data bottleneck, will take probably a while. Yeah, but it doesn't mean that, if you have maybe a smaller data set where the data set has some structure, yeah, some symmetry, that the quantum system recognizes better than a classical system. Yeah? Then you have the possibility to use it, of course.
Is there a split between inference and training? Because if you don't want to train a neural net on a classical computer and then run it on a quantum computer, then it's no longer a data problem, it's a compute problem.
It's a compute problem. Yeah, but that would be in the class of hybrid things. Yeah. That falls in that category of problems. For instance, with one of my PhD students, we looked at pulsar data of the SKA, and you can already now do a simple quantum machine learning algorithm that works on a dozen qubits to see is it a pulsar or not. Yeah? So it's a simple classification problem. Those kind of things you can still do. You can already do that. It's just the really huge data problems that are problems. Yeah? Okay, now, all these Googles and IBMs of this world and Microsoft, they are investing billions of dollars in these things. Yeah, so they have something in mind. Yeah, and what they have in mind is that there are really sorry, this is a very old slide. Yeah? That there are really big industrial and global problems that need to be tackled. Yeah, for instance, just an example in task discovery, if your quantum algorithm allows you to speed up the development of some pharmaceutical compound, a company can save hundreds of millions of dollars. Yeah? Because the trials and everything is very expensive. Yeah, so there is a huge potential for many kinds of applications. Yeah? For instance, the D-Wave annealing computer is already used in optimization problems, in finance problems, because it's really good at optimizing, finding kind of shortcuts. Yeah?
Training timetables?
Sorry?
Training timetables? Central Europe could use a lot of it.
Yeah, but the traffic optimization. You can those are kind of problems that you can map on an annealer. Yeah? So that those things you can do. But what is way more interesting is we all speak about the sustainable development goals. Yeah? And I have been involved for a couple of years now with the Geneva Science and Diplomacy Anticipator that try to anticipate technologies of the future. Yeah? And there's a special working group that aims at setting up an open quantum institute to make quantum computing accessible to the whole world. Yeah? But in order to convince the UN and government to open the wallets, yeah, you need to promise to be able to solve problems that have an impact. Yeah, and that's why over the years we came up with a few test cases of things that with current computers you can't. Now, there's a whole array of but for instance, new carbon capture materials. That's definitely, there are some obvious ones like better fertilizer. Yeah, fertilizer are expensive, but bacteria in the soil do for free, but we don't know how they. Yeah. So if we were able to solve that problem numerically, we could find a way to mix it together ourselves. Yeah. So this would be one of the problems. Yeah? Another problem for the antibiotics and wastewater, that trying to model it. It's very complicated. Yeah. Yes. 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 But,
it's actually a time-bound way to put it.
Yes. And sorry, I just mentioned the eco-friendly fertilizers. Yeah. You can't dump heavy chemicals in the ground forever. Yeah? At some stage, you need to come up with something else that helps us survive. Yeah. And this is one where I'm actively involved. Yeah, try to find first of all mathematical models. Yeah, to help find sustainable food production. Yeah? When climate is changing in countries that were growing something, you need to start thinking, what else can I grow? But then you need to know what could grow there. Yeah. And if it grows there, how do you transport it somewhere else? And so it's a really a nightmare. Yeah? And it starts also, how do you define nutritious people? You need to be able to quantify. If you want to address it numerically or computationally, you need to quantify. Yeah. So there are whole departments in the various UNESCO, UN that try to find kind of indices to quantify the nutritional value of, I don't know, of wheat and soya and whatever. And then, of course, the people tell you shouldn't eat carbohydrates, and so on and so forth. So it's a very complicated thing. Yeah? But this is one of the problems that we were trying to see whether, at least in principle, you can formulate it in such a way that when you have your 10,000 qubits, you can make a contribution. Yeah? And then, of course, during COVID, we will suffer from this. Yeah. And there are, of course, lots of variables that play a role. So it's not so difficult to come up with real problems that should have a numerical solution, and hopefully next generation computers will achieve it. But it will be up to the younger people, not up to me. Yeah. Yeah. So thank you very much. If you have questions, you know where to find. Yeah.
Thank you very much. So there were questions during the talk, but are there any questions now at the end? Yeah, please.
Maybe I missed that you brought up the idea of classical data and quantum data.
Yes.
Can you give us an example of what quantum data might be?
For example, if you have an optical table and you do something in photons, you have your quantum data in the photon, you just push it in the machine. Well, that should be easy. Yeah, in principle.
Well, if the data come in the same form as your quantum gadget, but so that can directly.
There are those 4 cases.
Yeah.
But at the moment, most people are worried on how I want to solve a problem in this world, this classical world, with the quantum computer. So that is what we want to do.
question that you asked, right, about trying to do the learning on the classical side. How easy would it be to translate that into a quantum? And that's
That's what the quantum neural networks try to do. Yeah, because quantum neural networks are essentially a variant of those variational algorithms that I showed, with various layers with many parameters. Yeah, and the optimization of the parameter happens classically. Yeah, then once you calculate the new parameters, you go back into the quantum computer. Yes, that's more or less probably what you are doing. Yeah.
Questions? That was me asking if there were other questions. I think there was a question here first. Okay.
Please.
I'm just curious. So quantum computers are obviously very good at simulating quantum systems.
Yeah.
But how, maybe this is obvious, but how good are they at simulating large-scale classical systems like weather? Weather is famously hard to predict. So is there?
You know, I showed you one of the things that they're good at is linear algebra.
Yeah.
But weather is not linear part of differential equation. Yeah. So at the moment, I'm not aware of any quantum algorithm to solve efficiently a nonlinear part of differential equation on a computer. Yeah. You can, of course, approximate it stepwise with normal differential that you can put together. But whether you get an exponential speed up is a completely different story.
Because there is a difference between classical chaos and quantum chaos, right?
Yes.
So maybe on a quantum computer, the quantum chaos can give you some kind of advantage.
Maybe. Yeah, no, you know, you want again something classical. Yeah. So I don't know, and there is no algorithm. If you look at that quantum algorithm zoo and search for other stalls, you won't find.
You mentioned that one of the students and some use quantum computing or 12 qubits to scan SKA data and pulsars.
Yes.
How does that compare to kind of the traditional machine learning, classical machine learning algorithms that are performing better? Is it the same?
It classifies fairly well. In fact, he is writing up the paper, so we will send it to you as it's possible. Yeah. But of course, you know, if you just want to, you can do it much faster, but you know, you have to start something. And it was quite fun. Yeah.
Any last questions? Okay, super. Well, if not, let's thank our speaker one more time.
Yep. Should I do that? Please. Stop recording.